I want you to imagine for just a second that you are standing right at the entrance of a massive, incredibly complex hedge maze.
Okay, a really big maze. Got it.
Right. And your goal is obviously to find the center. Now, if you tackle this maze the way our everyday devices do, I mean, the laptop on your desk or the smartphone in your pocket,
Hmm.
you wouldn't just look at the maze and try to, intuit the best path.
No, a standard computer wouldn't do that at all.
Exactly. You would methodically walk down every single possible corridor one at a time. You'd hit a dead end, turn around, walk all the way back, and then try the next one.
It's essentially a brute force approach, extremely methodical and, well, incredibly reliable. But depending on the size of the maze, it can be agonizingly tedious.
And that tediousness, that's really the essence of what we call a von Neumann computer architecture, right?
Yeah, exactly. That's the blueprint for almost all modern computing. It relies on strict, rigid, step-by-step logic.
But today, we are embarking on a deep dive into a complete paradigm shift. We are looking at a totally different way of solving that maze, which involves moving away from rigid logic and introducing something that sounds almost dangerous for a machine.
It really does.
We are talking about built-in physical randomness.
Which is, frankly, a tough pill to swallow for traditional engineers. I mean, we spend our whole lives trying to eliminate randomness from computers, to prevent errors.
Right. Nobody wants a random blue screen.
Exactly. But the research we are looking at today argues that controlled randomness, what physicists actually call entropy, is actually the key to unlocking the next massive leap forward in computational power.
And we have a seriously fascinating stack of notes to get through to explain this. Our mission today is to do a bit of, well, tech translation.
It's a heavy lift, but a fun one.
For sure. We are pulling from a highly technical, cutting-edge presentation from the Discover NSF Expedition Seminar Series. It was delivered by Professor Pedram Khalili at Northwestern University.
A fantastic presentation, by the way.
It really was. And our goal here is to take the absolute frontier of computer hardware and make it accessible to you. Whether you're an undergrad engineering student or a curious professional, or just someone who wants to understand the actual physics of our future devices, we're going to break this down.
And the core concept of Professor Khalili's seminar is the alternative to those von Neumann computers we just talked about. They're called probabilistic Ising machines, or PIMs.
Okay, let's stop right there. Probabilistic Ising machine. I mean, I know what probabilistic means, but where does the Ising part come from?
Oh, right. So it comes from a German physicist named Ernst Ising. Decades ago, he created this mathematical model to describe how atomic magnetic spins interact with each other.
Like tiny magnets on a grid.
Exactly like that. In an Ising model, you have this grid of tiny magnets, and they're all constantly influencing their neighbors. And depending on the temperature and the magnetic fields around them, they eventually settle into a collective state.
Okay, so they kind of chill out in the line eventually.
Yeah, exactly. And what modern researchers realized is that if you can actually build a physical version of this model, you can use that settling process to solve insanely complex math problems.
So instead of a computer running lines of code step by step, the physical behavior of the hardware is the calculation.
Precisely. But here's the catch. To make a computer probabilistic, to give it that necessary entropy, you can't just write a software program to simulate it.
Because that would just be the old von Neumann machine faking randomness, right?
Right, and simulated randomness takes way too much time and energy. You need a physical source of randomness built directly into the microchip itself.
You basically need like millions of microscopic physical coin flippers.
That is a great way to visualize it. I mean, in a standard computer, a standard bit is either a 0 or a 1. It's a coin sitting flat on a table, heads or tails.
Right, very binary.
But in a probabilistic computer, a p-bit is like a coin constantly spinning in the air. At any given microsecond, it has a probability of being a 0 or a 1. And the standard approach to building these tiny spinning coins has been to use a component called a stochastic magnetic tunnel junction.
SMTJ. Okay, we're going to hit a lot of acronyms today, so let's unpack this one. A magnetic tunnel junction. I am picturing two tiny magnets with something jammed in between them.
That's essentially it. Think of it like a microscopic sandwich. You have two slices of magnetic metal, and right in between them you have an incredibly thin layer of insulation.
How thin are we talking?
Oh, so thin that electrons can actually use a quantum mechanical trick called tunneling to just pop right through the barrier from one magnet to the other.
Man, quantum physics is wild.
Yeah.
And the stochastic part just means unpredictable, right? So this tiny magnetic sandwich is fluctuating randomly at room temperature.
Yes. The ambient thermal energy, literally just the heat of the room, is enough to make the magnetization of these tiny junctions wobble unpredictably.
So it's generating that beautiful, chaotic entropy that the icing machine needs to do its magic.
Exactly.
But wait, if SMTJs are the standard established way to do this, why aren't they in my smartphone right now? I mean, putting one or two of these on a chip is an amazing science fair trick, but putting billions of them on a chip to make a supercomputer, that seems to be the roadblock here.
It's a massive engineering hurdle. Scaling up these stochastic junctions is super difficult because they are incredibly sensitive. But the much bigger issue, physically speaking, is the support circuitry.
The stuff needed to read the coin flips.
Right. You have to translate those random wobbles into something the standard computer can actually understand.
Okay, I want to push back on this a little, or at least get an analogy going.
Yeah.
If I need a million tiny coin flippers, the problem isn't just making the coins right. The notes mention that scaling SMTJs requires duplicating area-intensive digital-to-analog converter elements.
Or DAX.
GACs, right.
Yeah.
So are the accessories required to make the tiny coin work actually taking up all the room on the chip?
You've hit the nail on the head. That is the exact bottleneck. If the p-bit is our spinning coin, the DAC is the massive machine required to read it.
But why is it so massive? The coin is microscopic.
Because reading an SMTJ traditionally requires flowing an electrical current through it. The resistance of the junction fluctuates in this analog wave. It's continuous, it's messy, and it's constantly moving.
And regular processors, yeet messy.
Exactly. A computer processor only understands digital signals clean, rigid ones, and zeros. So a digital-to-analog converter acts like a massive, clunky translation booth sitting right next to the p-bit.
Oh, wow. So I have this beautifully elegant microscopic spinning coin, but to actually use it, I have to build a giant translation booth next to every single one just to tell the computer whether it landed heads or tails.
Yep. You've isolated the exact problem. You simply cannot build a dense, efficient supercomputer if you are running out of physical real estate on the silicon wafer.
Because the translation booths take up the whole city block.
Exactly. If every single magnetic junction needs its own bulky DUE to translate the signal, the chip becomes enormous. Plus, it draws way too much power, and it just becomes economically impossible to manufacture at scale.
So we have a physical space problem, and it's driven by the fact that we are using electrical current to read the magnet. Which makes me wonder, if flowing current requires the giant translation booth, couldn't we just interact with the magnetic coin a different way?
What do you mean?
Like, instead of flowing electricity through it like a river, could we just use a static electric field?
You are touching on the exact mechanism of Professor Khalili's first major breakthrough discussed in the seminar.
Oh, really? Awesome.
Yeah, they realized that if the old coin flippers and their bulky detranslation booths were taking up too much space, they had to invent a completely new type of junction. Enter the voltage-controlled magnetic tunnel junction, or VMTJ.
Okay, tech translation time. Let's break down how VMTJs solve this space issue. The source says the magic here relies on something called the VCMA effect.
Voltage-controlled magnetic anisotropy.
Right. Now, anisotropy is one of those words that sounds incredibly intimidating. But it basically just means a built-in preference, right? Like wood having a grain, or a heavy door wanting to stay shut.
That is the brilliant way to think about it. In these nanoscale magnets, anisotropy is just the material's natural preference to have its magnetic field point in a specific stable direction. It wants to stay closed, just like your heavy door.
And when there is no voltage applied, these VMTJs are completely thermally stable. The door is shut, the coin isn't spinning, it's just resting on the table.
Exactly. But the VCMA effect changes all of that.
So what happens when you turn it on?
Well, when you apply a static voltage and think of this as electrical pressure rather than a flowing river of electrical current, you alter that preference. You effectively remove the hinges from your heavy door.
Oh, I like that.
Yeah, you lower the energy barrier so much that the ambient heat of the room is suddenly enough to swing the door wildly back and forth. You have officially turned on the randomness.
And because we're just using static voltage to lower the barrier, we aren't pumping current through it in the same messy way. So what does that mean for our giant translation booths?
It means we can throw them out completely.
Wait, really? Just gone?
Just gone. This is the absolute game changer of this research. Because they use voltage, they can synchronize the random fluctuations with the computer's internal clock. They generate the random bits synchronously, pulling the signal straight into the digital circuitry.
We bypass the translation booth entirely. It just plugs straight into the digital circuit. That must completely change the physical footprint of the chip.
Oh, absolutely. You could pack millions more of these onto a single wafer. It is a massive leap in miniaturization.
That's incredible.
And the best part is, this isn't just theoretical physics happening on a chalkboard somewhere. Professor Khalili's team actually fabricated an ASIC, an application-specific integrated circuit, to prove this really works.
Yeah, the notes mentioned they built this using standard 130-nanometer foundry CMOS. Now, for you listening, CMOS is just the standard process we've used to build computer chips for decades. But 130 nanometer isn't exactly the newest, smallest chip size, right? I assume that's entirely the point.
It is entirely the point. Look, if you invent a revolutionary new technology, but it requires a brand new $10 billion experimental fabrication plant to build it.
And that's never going to happen.
Right, it might never see the light of day. But by successfully building these VMTJs using older, standard 130 nanometer CMOS technology, they proved manufacturability. They proved this new magnetic technology can be bolted right onto the legacy semiconductor infrastructure we already have.
They linked up 1,143 of these probabilistic bits, and they gave this chip a real-world test, which was integer factorization.
A classic test.
Now, factoring numbers sounds like middle school math. I mean, if I ask you for the prime factors of 15, you just tell me it's 3 and 5. Why is this the ultimate test for a new supercomputer?
Because while factoring 15 is easy, factoring a 300-digit number is the mathematical bedrock of modern encryption. It protects your bank accounts, your emails, literally everything.
Right. It's what keeps the internet secure.
Exactly. And a classical von Neumann computer, factoring a massive number like that might take thousands of years. It has to try every single path in the maze, dividing by every possible prime number until it finds a match.
It's just grinding combinations until the heat death of the universe.
Yeah, pretty much. But a probabilistic Ising machine using these VMTJs approaches the problem completely differently. Remember how we said the physical behavior of the hardware is the calculation?
Yeah, the physics does the math.
Right. They literally wire these p-bits together so that the physical magnetic interactions represent the math problem itself. They map the factorization problem onto what we call an energy landscape.
Okay, this is where we bring the maze analogy back. So instead of walking down every single path in the maze, one by one, the Ising machine essentially floods the entire maze with water. And the water instantly, naturally flows to the lowest point, which is the exit.
That is exactly what happens. In physics, systems naturally want to rest in their lowest energy state. Think of a ball rolling down a hill.
It naturally finds the bottom.
Exactly. So when you let these 11,143 magnetic coins fluctuate and then you gradually freeze them, they physically settle into the configuration that requires the least energy. And because of how they're wired, that lowest energy state is the mathematical answer.
The physics literally does the math for you.
Yes. Proving that VMTJs can achieve this without the bulky DACs is a total watershed moment.
So space is solved. We got rid of the translation booths. But hardware engineers are never fully satisfied, are they?
Never.
Space is only one part of the equation. There's always the pursuit of speed, heat reduction, and even greater density. Which brings us to a really, counterintuitive part of Professor Khalili's presentation.
Yeah, moving beyond VMTJs to explore a second class of unconventional junctions. The all-antiferromagnetic tunnel junctions, or ATJs.
I have to admit, when I was reading through the source material, I totally tripped over the terminology here. The specific material they used is let me make sure I have this right, a non-collinear antiferromagnetic material called platinum manganese 3.
That's the one.
My question is right there in the name. Antiferromagnetic. If it's anti-magnetic, how is it a magnet? This sounds utterly useless for building a magnetic memory device.
It does sound like a total paradox. I mean, to understand why it's brilliant, we have to look at what magnetism actually is at the atomic level.
Okay, take us down to the atoms.
So in a normal ferromagnet, like the magnet holding up a takeout menu on your refrigerator, all the tiny atomic magnetic moments are pointing in the exact same direction.
Right, they are all pulling together like a highly coordinated tug-of-war team. They combine their strength to create a large magnetic field that you can actually feel.
Precisely. But in an antiferromagnetic material, the atoms are arranged so that their magnetic moments alternate. One points up, the next points down, the next points up.
Oh, I see. They are playing tug-of-war against themselves.
Yes. And they do it so perfectly, in fact, that they completely cancel each other out. So microscopically, the material appears to have no magnetic field whatsoever. It wouldn't stick to your fridge at all.
So it's essentially invisible magnetism. Why on earth would we want to build a computer out of invisible magnets?
For two massive reasons.
Hmm.
First, because they don't produce a stray magnetic field, they don't interfere with their neighbors.
Oh, because normal magnets would push and pull on each other if they got too close.
Exactly. But with these, you can pack them incredibly close together on a chip without them accidentally flipping each other. There's zero crosstalk.
Okay, so extreme density, what's the second reason?
Speed. Because antiferromagnets are locked in this tight alternating grid, the physical tension between the atoms is incredibly high. Think of a tightly strung guitar string versus a really loose one.
The tight one vibrates way faster.
Right. When you pluck the tight one, the antiferromagnet, it vibrates incredibly fast. They operate at terahertz frequencies, whereas normal ferromagnets only operate at gigahertz frequencies.
Wow, so they are orders of magnitude faster.
Blisteringly fast.
So they are blisteringly fast, and you can pack them tightly because they are magnetically invisible. But that brings up a really obvious problem.
Which is?
If they're invisible,
Yeah.
how do you talk to them? I mean, how do you write data to a magnet that won't respond to a normal magnetic field?
This is the second major breakthrough from the Northwestern team. They didn't just use any plain antiferromagnet, they used a non-collinear one.
Non-collinear. What does that mean in this context?
It means the magnetic moments don't just point strictly up and down. They form a complex, three-dimensional geometric pattern, specifically an octupole order.
An octupole order.
Yeah, think of it like a highly complex 3D knot of magnetic fields. And the team discovered a brand new physical mechanism to control it called octupole-driven spin transfer torque, or OTT.
Octupole-driven spin transfer torque. Okay, let's translate that for everyone.
Essentially, they found a way to use a highly specific electrical current that acts like a specialized wrench. It perfectly fits this 3D invisible magnetic knot and allows them to twist it.
So they can finally grab the invisible magnet.
Exactly. This new OTT mechanism allows them to switch the complex magnetic order electrically, which was previously thought to be incredibly difficult, if not impossible.
And the result of using this special wrench. The notes highlight a massive achievement here, a room temperature tunneling magnetoresistance ratio of over 300%.
Which is huge.
Let's break that down. Tunneling magnetoresistance, or TMR, is basically the signal-to-noise ratio, right? It's the clarity of the readout.
Yeah.
It's how easily the computer can tell if the junction is in a 0 or a 1 state.
Exactly. When the magnet flips, its electrical resistance actually changes. TMR is the measurement of that change. And in the world of antiferromagnets, signals are usually notoriously weak.
So is 300% good.
Over 300% at room temperature is deafeningly loud. It's a massive, clear signal. It essentially proves that we now have a material that is ultra-fast, ultra-dense, and produces a readout that is practically impossible for the computer to misinterpret.
It is genuinely staggering. I mean, we are manipulating the complex geometric arrangement of invisible atomic magnetic moments just to build a computer that floods a mathematical maze to find an answer.
It sounds like science fiction, but it's happening right now.
Which naturally makes me wonder about the mind translating all this physics for us today. Professor Pedram Khalili.
Yeah, his resume is exactly what you would expect for someone pioneering a whole new field of hardware architecture.
I bet.
He's an electrical and computer engineering professor at Northwestern. He holds a PhD cum laude from Delft University of Technology. He has over 140 peer-reviewed papers and 18 U.S. patents.
That's quite a list.
Oh, and he also directs the Physical Electronics Research Laboratory.
But, you know, the reason this seminar was such a perfect candidate for our deep dive today isn't just because he's a prolific researcher. It's because he is an elite educator.
That's a really good point.
He won the 2020 Alan Taflove Best Teacher Award and was actually named an IE Nanotechnology Council Distinguished Lecturer.
Why does the educator aspect matter so much in this specific context? I mean, beyond just giving a good seminar.
Because you can invent the greatest, fastest microchip in the history of the world in a vacuum. But if you cannot explain how to use it to the next generation of engineers who, by the way, have spent their entire lives being drilled in strict step-by-step von Neumann logic, the technology will just die in the lab.
So it's not enough to build it, you have to teach people how to think about it.
Exactly. A paradigm shift requires retraining an entire industry. Educators like Professor Khalili are vital because they are actively bridging the gap between abstract quantum physics and practical engineering. They're teaching the tech world how to stop walking the maze and start seeing it entirely differently. So as we wrap up, what does this all mean for you listening today? Let's just recap the journey we've been on.
It's been a long one.
It really has. We're watching the sunset on the strict, rigid rules of standard computing, at least when it comes to solving the world's most complex optimization problems. By harnessing the tiny, unpredictable, chaotic physics of magnets, researchers are building a totally new reality.
Step one was the VMTJs.
Right. First, through voltage-controlled magnetic tunnel junctions that eliminate those bulky translation booths, and next, through ultra-fast, magnetically invisible antiferromagnets. They are building probabilistic computers designed to guess, check, and solve massive problems faster and more efficiently than we ever thought possible.
We are quite literally teaching sand and metal to think probabilistically.
Which leaves us with a genuinely provocative thought. Something I really want you to mull over as you go about your day.
Oh, lay it on me.
For decades, a computer error has been defined as a deviation from strict mathematical logic, a glitch, a mistake.
Right, a failure of the system.
But if the supercomputers of the future literally rely on physical organic randomness to function, what happens to the concept of an error? If a machine is fundamentally designed to guess based on probability and energy landscapes, rather than following a rigid script, does the line between a computer's programming and a human's intuition start to blur?
It is a profound philosophical shift. I mean, when randomness is the actual engine of your intelligence, unpredictability is no longer a bug. It becomes the defining feature.
I couldn't agree more. The next time you feel like you are wandering blindly through a maze, hitting dead ends, just remember, somewhere in a lab at Northwestern, they are building a tiny, invisible, spinning magnetic coin that can flood the whole maze and see the exit from above. Thanks for joining us on this deep dive. We'll catch you next time.